Okay, we are back with lesson 9, Taylor and Maclaurin series. And what we did on this last one that I just got finished with, I wanted to just remind you on example number 2, you evaluated the indefinite integral as a power series, and you found the radius of convergence, because we knew that for something to converge with the ratio test, that your variable had to be, your answer to your limit had to be less than 1. And when your limit has your variable in it, then you can find what your variable needs to be convergent. Okay, so we used that to find that radius of convergence. Another way to write that radius of convergence would be t between -1 and +1. Okay, that's another way to write it. All right, let's go to our next example. When differentiating a Taylor series, just like the derivative term by term, or just take the derivative term by term, the radius of convergence of the derivative will be the same as the original series. However, the interval of convergence could change. Be sure to check the endpoints. Okay, so we're going to have a situation where we're going to have to do that coming up here. I don't know if it's this next example, but I know it is coming up where we have had to check those endpoints. I can't remember if it's this one, but differentiate to find a power series representation and radius of convergence for f of x equals 1 over 1 plus x quantity squared. So again, we're going to recall that 1 over 1 minus x is going to be equivalent to that summation from n equals 0 to infinity of x to the n. So when I put 0 in, I get 1. When I put 1 in, I get x. When I put 2 in, I get x squared. When I put 3 in, I get x cubed, ... Okay? Now, also, think about what the derivative of this is, because you should always be thinking about, what if I took the derivative of this? Well, if I was going to take d dx of 1 minus x to the -1, I would take and bring the -1 down times 1 minus x to the -2 times the derivative of 1 minus x. So that -1 times -1 is a +1 over 1 minus x quantity squared. Now, the only thing that changes on this one is that it's 1 plus x squared, okay? So I'm thinking, okay, is this going to be close to if I took the derivative of 1 over 1 plus x? And how would that change my Taylor polynomial also? But because you can remember that if you wanted to use this one, you could say that this was 1 over 1 minus a minus x, and you could put a negative x in for these values. So I could say, okay, 1, and then I would say minus x plus x squared minus x cubed plus ... Okay, so by doing 1 plus x, it's going to put a -1 to the n in front of it. And this would be from n equals 0 to infinity if you did -1 to the n times x to the n, which is basically just your -x to the n, which is what you were doing, what you were changing it by. But if I had 1 over 1 plus x and I was going to take the derivative, my derivative is of 1 plus x to the -1. So this would be -1 times 1 plus x to the -2 times the derivative of 1 plus x, which is just 1. And so this becomes -1 over 1 plus x squared. So really the derivative, if I took the derivative of everything in my summation, my Taylor polynomial here for 1 over 1 plus x, if I took the derivative of everything, I should get the exact negative of the actual derivative. So what we're going to do is we're going to say, well, I need to take the derivative of 1 over 1 plus x, because that is going to be, I'm going to be on my way to getting the Taylor polynomial for this f of x. And so we said that 1 over 1 plus x was 1 minus x plus x squared minus x cubed plus dot, dot, dot. And it is equivalent to the summation n equals 0 to infinity of negative 1 to the n times x to the n, okay? Well, if I'm going to take the derivative of that, I'm going to take the derivative of this. And so I'm taking the derivative of both sides. So I probably shouldn't have put that d dx here right at the beginning. I should have just started it as 1 over 1 plus x is equivalent to, and then taken the derivative of both sides. So sorry about that. I was looking at my notes and that's what it looked like, and then I realized why it looked like that. So this one's going to be negative 1 over 1 plus x squared is equal to, and now if I take the derivative, I get negative 1 plus 2x minus 3x squared plus dot, dot, dot. And the derivative of your summation with respect to x, this doesn't have an x in it. Negative 1 to the n doesn't have an x in it, so that just stays the same. You're going to bring the n down times x to the n minus 1. So that's going to be your derivative of your summation. And then, since we don't want negative 1, we want positive 1, now we're going to multiply each side by negative 1. And of course, that needs to be distributed all the way through. So this is going to be 1 over 1 plus x squared is equal to positive 1 minus 2x plus 3x squared minus dot, dot, dot. And then you've got your summation, n equals 0 to infinity. We are adding a negative 1 onto this negative 1. And now we're going to bring this down. So we've got our Taylor polynomial for our 1 over 1 plus x quantity squared, or power series, I guess I should say. We've got our power series. And if we want to make sure that this converges for certain x values, or we want to see what x values it converges for, we're going to use the ratio test. And so we're going to look at the limit as n goes to infinity, absolute value of. So where is it? Here it is. The one that we are looking at is this right here. And so we're going to say n plus 1 times x to the n plus 1 minus 1. And then we're going to divide by n x to the n minus 1. Limit as n goes to infinity. And this one's going to be n plus 1 x to the n over n x to the n x to the negative 1. My x to the n's are going to cancel. So now I have n plus 1 over n times x. Okay? I can separate these, but this one, as n goes to infinity, this goes to 1. So you're going to be left with this, and we're saying that if this is less than 1, then it converges. So our radius of convergence for this one is also going to be 1. And that means that, you know, anything between -1 and +1. Okay. So that was your radius of convergence there. So now let's go to example number 4. We can also integrate Taylor series term by term, given that integration is the inverse operation of differentiation. Example 4, find a power series for f of x equals the inverse tangent of 2x using substitution and integration. All right, so for example number 4, we're going to look at the integral of, and if this was inverse tangent 2x, the derivative is 2 over 1 plus 4x squared dx. And so if you bring your 2 on the outside, integral 1 over 1 plus 4x squared dx. So remember, you need to know and recall that the derivative of inverse tangent 2x is equivalent to 2 over 1 plus 4x squared. Also, the inverse tangent of 2x plus c is my integral of 2 over 1 plus 4x squared dx. Okay, so those two functions are connected to one another. They are like inverses of one another. And so we're looking for a power series. Well, what do we know? Well, this power series looks like 1 over 1 plus x. Okay? And we said that 1 over 1 plus x on the last one was equivalent to, where am I? 1 minus x plus x squared minus x cubed plus ... summation n equals 0 to infinity -1 to the n times x to the n. That was our 1 plus x, because our 1 over 1 minus x, that was our 1 over 1 plus x. Our 1 over 1 minus x was 1 plus x squared plus x cubed plus ... summation n equals 0 to infinity of x to the n. And so the only thing that changed, this was minus a minus x. And so you now have negative x to the n. But now here, this is 2 times the integral of 1 over 1. This is like plus, and then here's your 4x squared. That is your x. So you've got 2 times. So I'm going to put 4x squared into this wherever I see an x. So this is 1 minus, this would be 4x squared, plus 4x squared squared, which is going to be 16 sorry, I was looking at something else. 16x to the 4th, and then minus 4x squared taken to the 3rd power, 64x to the 6th, plus ... which our summation then becomes summation from n equals 0 to infinity. This still is changing from plus to minus, but this summation is going to be instead of negative 1 to the n, it's actually going to be negative 4 to the n. Because negative 4 to the 0 is 1. Negative 4 to the 1, negative 4. Negative 4 to the 2 is 16. Negative 4 to the 3 is negative 64. So if we put in here negative 4 to the n, that will give us all of our terms. And now we need to get our x's. So this is going to be x to the 2n, because this one is x to the 0, x to the 2, x to the 4, x to the 6. And then that right there is our summation. Now, since we were integrating this, we said that this was equivalent to 2 times the integral of this, which should be equivalent to 2 times the integral of this summation. Which should be equivalent to, I'm going to change colors because we are going to have to go down here like that, which should be equivalent to 2 times the integral of the summation n equals 0 to infinity, negative 4 to the n, x to the 2n dx. And so our inverse tangent of 2x plus c is equivalent to 2 times the summation from n equals 0 to infinity, negative 4 to the n times x to the 2n plus 1 over 2n plus 1 plus c. Well, those c's are going to cancel. And then that will give us our equivalency for inverse tangent of 2x. The summation, I want to put this 2 on the inside. And when I do that, I'm going to put it in with this 4 right here. So I think I need to add another page so that I can bring this down, and we're going to say that the inverse tangent of 2x is equivalent to summation n equals 0 to infinity. This is going to be negative 1 to the n. Then I have a 4, which is going to be 2 squared, and then another 2. Somehow I got 2 to the 2n plus 1. I'm going to have to look at that again. So I had 2 times the summation from negative 4 to the n, x to the 2n plus 1 over 2n plus 1. And I wanted to put that 2 through. And I know I brought out my negative 4 to the n. Oh, there we are. There's your 2 squared to the n. That's 4 to the n. And then this is times 2, so it'd be 2 to the 2n plus 1. So this was your 4 to the n. It became 2 squared to the n, and then we multiplied by 2, and we simplified to 2 to the 2n plus 1. And so this ends up being your power series. And then the next thing that we talk about is the binomial series. So the last series we want to develop is for a function of the form f of x equals 1 plus x to the k, which is called the binomial series. If k is any number and the absolute value of x is less than 1, then 1 plus x to the k is the summation from n equals 0 to infinity, k choose n, x to the n, which is equivalent to 1 plus kx plus k times k minus 1 over 2 factorial x squared plus k times k minus 1 times k minus 2 over 3 factorial times x cubed dot dot dot. The radius of convergence is 1. So now, find the Maclaurin series for f of x equals 1 over 1 plus x to the fourth. Well, now they're telling us that, hey, this is a binomial series. So this is what you can use to solve for this. So I'm going to take that 1 plus x to the negative fourth and say that it is equivalent to summation n equals 0 to infinity. Negative 4 choose n, x to the n. And so that one is going to be 1, and then minus 4x plus negative 4 times negative 4 minus 1 over 2 factorial x squared plus negative 4 times negative 4 minus 1 times negative 4 minus 2 over 3 factorial times x to the third plus dot dot dot. And so this is going to be equivalent to, if I simplify it, 1 minus 4x. This is going to be negative 4 times negative 5 is positive 20 divided by 2 is 10, x squared. This one's going to be negative 4 times negative 5 is positive 20 times negative 6. Well, that negative 6 is going to cancel with this 3 times 2 times 1. So that's going to give us negative 20x cubed. And then plus dot dot dot. This is going to be our Maclaurin series for 1 over 1 plus x to the fourth. Okay. And then example number 6. This is our last one. Approximate the integral from 0 to 1 x cosine x cubed dx to within 3 decimal places. So the first thing we're going to do is find a power series for y equals x cosine x cubed. So cosine x cubed, summation n equals 0 to infinity, negative 1 to the n. This is, normally this would be x to the 2n divided by 2n factorial, but since our x is now x cubed, we put the x cubed in, and now we'll simplify. Okay, so that was our step 1. Now, if we then multiplied by x, this is going to be x to the 6n plus 1. And now we want to integrate. So second thing we're going to do is integrate. So we want to integrate from 0 to 1, x cosine of x cubed dx is equivalent to the integral from 0 to 1 of the summation n equals 0 to infinity, negative 1 to the n, x to the 6n plus 1 over 2n factorial dx. So integration. With respect to x. So anything that is like negative 1 to the n, it stays the same. But if you're integrating with respect to x, you're going to take your x to the 6n plus 1, so that's going to be x to the 6n plus 2. You're you're going to divide by 6n plus 2, and this 2n factorial is going to stay the same from 0 to 1. And when we put the 1 in, 1 to the 6n plus 2 divided by 6n plus 2 times 2n factorial minus summation n equals 0 to infinity of 0. And so once you do that, this is going to look like an alternating series, right? And we can use that alternating series test. So by the alternating series test, or actually I put the alternating series estimation theorem, the estimate is at most the absolute value of the first unused term. So let's expand it. Okay, I'm going to add a page again. We've got our summation from n equals 0 to infinity, negative 1 to the n over 6n plus 2 times 2n factorial is equivalent to, okay, if I put a 0 in for n, I get 1 over 2. And then if I put a 1 in, I get negative 1 over, and that would be 8 times 2, 16. And you might want to, before you start simplifying it, 8 times 2 factorial. You might want to do it like that at first. And so when n is 2, you get positive 1 over, this would be 14 times 4 factorial. And then n is 3, you get negative 1 over that would be 20 times 6 factorial. And you could say plus dot, dot, dot. And then let's go ahead and clean it up a little bit. 1/2 minus 1/16 plus 1 over 336 minus 1 over 14,400 plus dot, dot, dot. These first 3 values, if you added those up on your calculator, you would get 0.440. Therefore, the estimate is correct to 4 decimal places. By the alternating series theorem, and 1 minus 1 over 14,400, that absolute value that's not a 1. That was an absolute value sign. I was like, wait a minute, why do we do 1? Just this term, the absolute value of this first unused term is approximately 0.00007. And that's what showed us that 4 decimal places for the error.